Hello, I'm Chris, this is Blake, like Dr. Ken said. So today we're going to be telling you guys about information retrieval using the singular value decomposition. And that sounds scary, but basically what it means is we're going to be describing how the library, its search catalog, uses linear algebra to find books for you.
This is a typical library search. You input the keywords that you want to search for in the search bar. You indicate where the keywords will occur, and the library retrieves a list of relevant books for you. Now, it's pretty convenient, but how does it actually work? You might think that the search engine goes through every single book, searches every single word of every single title, and returns any book that has the relevant word in it. That is the right idea, but it's not exactly how it works, but we're going to explain that just now.
Okay, so here's a really, really small example of how the library takes the books in the library and codes them using this matrix. So me and Blake built a 4-book library. These are the 4 books on the sides, and the way it does it is it makes each column a book, okay? And you've probably already figured out how to read this matrix. The words are going to be the rows. Those are all distinct words. That's important. They're distinct words. And the way each column works, each column represents a book, and there's going to be a 1 in each spot where a word appears in the title of the book. So that 4th column, that yellow book, is representing A Clockwork Orange because a 1 appears in A, 1 appears in Clockwork and Orange, and 0s elsewhere. So the important thing to take away from this is that each column is a book. Okay, that's the main thing. Each column vector in this matrix represents a book, and that's important because vectors are great, and we can represent a vector as a line in space, as Blake will now show.
So this is a quick schematic. This is not what it actually looks like because it's way too complicated to draw out, but this is a good representation to help us understand what's happening. So whenever you input a search into the search bar, it's also a vector, and we represented that with the red vector here. So it points in a certain direction. That's what's important about the vectors, they have a direction. Any relevant books will be in nearly the same direction as your search vector. So by changing this little white circle, it's like our user tunable parameter. We can specify if we want a more specific search, a less specific search. We can pour more books or less books. And that's pretty much the conceptual idea behind vector space. But as we'll see, this gets messy.
Yes, so in our example, we only had 4 books, okay? And they had really short titles. 3 of them had 2-word titles. And we had 7 rows, okay? So after doing more research, me and Blake did discover that the library has more than 4 books. And so the picture idea doesn't work because each row represents a word that appears in the title of this book. But the problem with thinking about it as a vector space is each row is going to be a new dimension. So even with our 4-book library, we had 7 dimensions. So it doesn't work. We can't look at the vector space. It's unimaginable, right? So we go back to the matrix idea. So like I said, the way the matrix works is each column represents a book, and each row represents a distinct word. So to represent this entire library, we're going to have a massive matrix, right? However many thousands of columns for each book, and then basically the entire English language along the rows. So even using the matrix, it's still a huge amount of data. All right, and this problem of getting a computer to search through this much data is a real fundamental issue in all sorts of topics nowadays.
So in comes what we call latent semantic indexing. Latent semantic indexing utilizes a mathematical concept known as the singular value decomposition of the matrix. Basically, it factors the matrix, much like you can factor a number, into component parts. So that way the data is more manageable and easier to analyze. Now the important matrix is this middle one here, the S matrix. This contains what we call the singular values. Now these singular values are very important because they have an order to them. The most relevant singular value is the one at the top left. The least relevant singular value is the one at the bottom right. Using this information, we can do a little dirty trick and we can get rid of a bottom percentage of these values. And by turning these bottom values to 0 and recombining the three matrices, we get something that looks almost nothing like this, but behaves exactly the same and makes your searching extremely streamlined. So it's very efficient, but it loses kind of the beauty of the zeros and ones, but it really helps the computer out a lot.
Okay, so Blake kind of just gave a really brief description of the math behind SVD, sort of really brief. But what is actually going on with that nice matrix that we had? It made a lot of sense. Like I said, the books were columns and we had words along the rows. And you can imagine this massive matrix representing the library. It's nice, right? But by using the SVD, what we do is we've automatically associated related words in the matrix and condensed it down automatically. So we tell the computer to do this, and it does it for us, and it relates words and just squishes the matrix down, makes it smaller, makes it more efficient, makes your search faster without manually going in there and telling the computer which terms are related.
So the big thing to take away here is that big data is everywhere in our modern world. And the first line of attack against big data is breaking it down into manageable parts. The SVD is the poster child of this. It breaks the matrix into three nice chunks. The middle chunk has most of the information, and the other two chunks just represent a little bit more information. It has applications to the fields all across the world. Image compression is a good one. Information retrieval and any other field that deals with a large amount of data can utilize the SVD to make their data more manageable.
Thank you guys for coming. For listening.